Welcome to the 9th session on electrolytic conductance, and in this we will be dealing with activities, mean ionic activities of electrolytes. So, we will be dealing with both activities and mean ionic activities. Now, why do we consider the activities as well as mean ionic activities? We know that in concentrated solutions, always the concentration what we observe and that which is calculated theoretically, it varies a lot. So, due to this, the term activity was introduced, so that the difference between these two, that is in concentrated solutions, that is the calculated and the theoretical values, the deviations can be explained introducing activities and mean ionic activities. We know that in concentrated solutions there will be inter-ionic attractions, and these interactions are responsible for deviation from ideal behavior. Now, let us see what are activities and activity coefficients of electrolytes. Here we are going to take an electrolyte which is an univalent electrolyte, both B as well as A are univalent. Okay. The ionization I have written it as B plus and A minus, thinking that B is a cation and A is a anion. Now, when we apply the equilibrium constant, because this is existing in an equilibrium, K is equal to activity of B plus into activity of A minus divided by activity of BA, that is the activity of the electrolyte, where A stands for the activities of the species which is shown by the subscript. See, here we have written B plus, which shows that it is the activity of the ion B plus. When we say A with A minus, it means that it is the activity of the ion A minus, and activity of BA stands for the activity of the electrolyte. Now, activity of a substance is considered as the product of concentration of that substance with activity coefficient. That is, activity is equal to the activity coefficient represented by the Greek alphabet gamma. Activity A is equal to gamma into M, where M is the concentration, usually it is molality. Okay. So, this is how activity is related to concentration, and usually that concentration is molality by a factor activity coefficient. Okay. Now, this activity coefficient, it gives us a measure of departure of a substance or an electrolyte from an ideal behavior. Now, when we substitute this for activities in the above equation 1, you get K, the equilibrium constant, is equal to activity coefficient of B plus into molality of B plus into activity coefficient of A minus into molality of A minus divided by activity coefficient of the electrolyte BA and molality of the electrolyte BA. Now, what we are going to do is we will just rearrange so that activity coefficients are put together and molalities together. So, here we have activity coefficient of B plus into activity coefficient of A minus divided by activity coefficient of the electrolyte BA multiplied by molality of B plus into molality of A minus divided by molality of the electrolyte BA. Now, when we consider weak electrolytes, we are considering weak electrolytes and they are only partially ionized, and therefore, their concentration will be very low. And if the concentration is low, there is a dilute solution, and therefore, they do not deviate appreciably from ideality. In such cases, the activity coefficient factor vanishes, or you can say that the activity coefficient factor will be equal to unity. In that case, you can say that is the activities as well as molality, which is the concentration term, they become equal. Okay. But in the case of strong electrolytes, this is not the case. You can say that there will be considerable deviation due to inter-ionic attractions. In such cases, the activity coefficient differs from unity and it will be having a certain value, and therefore, activities will not be equal to the concentration, that is the molality of the electrolyte. Next, we will see about the mean ionic activity. Why do you go for mean ionic activity? We know that activities or activity coefficient. Suppose I am having an electrolyte sodium nitrate. Okay. If I have to find out the activities or activity coefficients of sodium alone, that is, you will have to take sodium ion. Here the difficulty is you cannot prepare an electrolytic solution which contains sodium ion alone. It will be always associated with the anion. It can be either sodium nitrate or it can be either chloride, whatever it is. In that case, you can't measure the activity coefficient or activity of sodium ion alone. That is one point. Another thing is the activity of sodium ion is dependent on the anion with which it is associated. So, you cannot eliminate that and find the activity coefficient or activity of sodium ion. So, in that case what we do is we actually take sodium nitrate as such, and from that we introduce a term known as mean ionic activity, and from mean ionic activity it is related to concentration with respect to mean ionic activity coefficient, because in the other case we were saying that activity is related to molality, that is when it is multiplied by activity coefficient gamma. So, when we are taking mean ionic activity, the activity coefficient will also be the mean ionic activity coefficient, that is the only difference. Now, here you can say that suppose you are having an electrolyte in which we have a cation and an anion, and their activity is represented as A plus and A minus. The mean ionic activity is the geometric mean, that is you have to take the product of activity coefficient of the cation raised to the power x if it has got x moles into activity coefficient of anion raised to the power y if anions are produced y moles from the electrolyte. So, you can define mean ionic activity as the geometric mean of the activities of the component ions. So, that is how we find out the mean ionic activity. Let we have an electrolyte which is a univalent Ba. This ionizes as B plus and A minus. The mean ionic activity of an electrolyte is given as A is equal to A plus or minus into A, here it is plus or minus, which is equal to A plus into A minus. That is, when we multiply these two values, you take the square and you take the square root, and then you will get the value of A plus or minus. Here we will be getting the square, and if I want the value of A plus or minus, that will be square root of A plus or minus whole square, that is equal to A plus or minus. This is known as mean ionic activity. So, we are going to take the mean ionic activities. Here, see, we are going to take an electrolyte. Here we were taking it as univalent, but it need not be the case always. Let us consider a YX electrolyte. So, it is represented as BX and AY. Okay. This ionizes as there will be X moles of B, the valency of B is here. So, Y plus Y moles of A to the power X minus, because the valency of A is written near B. Okay. Now, if I start with 1 mole of this electrolyte, I will get X moles of By plus and Y moles of Ax minus ions. See, here we have X, B will be X times, and therefore, that is By plus. Y plus shows that it is the charge on that ion. So, that is equal to X times, and in the case of A, it will be Y times, because we are having Y moles in this 1 mole of electrolyte. Now, if that is the case, the activity of the electrolyte will be equal to activity of the cation. This cation represents A plus, means that is B raised to the power Y plus, and A minus stands for A raised to X minus. Okay. So, to make it simple, I put it as A plus raised to the power X. Why? Because there are X moles, into A minus raised to the power Y times, because there are Y moles of it, and you can put it as mean ionic activity raised to the power X plus Y, the powers added. Now, if you have to find out the activity or mean ionic activity coefficients or whatever it is, what we do is we either do it by measuring the EMF or by measuring the colligative properties. These are the two methods to determine activity as well as mean ionic activities of an solution, especially electrolytes. Now, we will go for mean ionic activity coefficient. Now, again we take the similar electrolyte which dissociates at X into B to the power Y plus Y into A X minus. Here the activities will be given like this, that is, I am taking the mean ionic activities raised to the power X into mean ionic activities raised to the power Y. Okay. But the mean ionic activity, how is it related to the concentration? We know that activity is related to concentration as gamma into m. As I have told you earlier, here we are taking mean ionic activity, and therefore, gamma, that will be the mean ionic activity coefficient into molality. Now, let us write the expression for that, that is activities of A plus or minus raised to the power X will be activity mean ionic activity coefficient into X times molality. Why is it so? Because we know that in the case of cation, that is molality of cation, will be X times m, where m is the molality of the electrolyte. Okay, that we have been dealing a bit before, that is again A x minus molality will be Y times m, because X moles of By plus ions will be produced as well as Y moles of A x minus ions will be produced by dissociation of that electrolyte. So, you have to put the molality as X m whole raised to the power X. Again mean ionic activity coefficient into Y times m, which is the molality of the A x minus ion raised to the power Y times. Now, that is equal to, you put X and Y, X raised to X, Y raised to Y, that is taken out, and mean ionic activity coefficient into molality whole raised to x plus y for 1 electrolyte. X is the valency, that is 1, y is also 1, and therefore activity is equal to mean ionic activity square into m to the power 2. For a 2,1 electrolyte or 1,2 electrolyte, activity is equal to mean ionic activity cube into m to the power cube, because here it comes 1 plus 2 and 1 plus 2. If activities are determined experimentally by EMF measurement or colligative property, as I have said earlier, mean ionic activities can be easily calculated since x and y are known. X and y are known, then you can find out the mean ionic activities. Now, let us see the values of mean ionic activity coefficients of sodium chloride at 298 Kelvin, or you can say that is 25 degrees Celsius. Now, if you go through this, you can see that the molality of solution is 0.001. Its mean ionic activity coefficient, this is the values of mean ionic activity coefficient, is 0.966. When it is 0.005, it has been increased, it becomes 0.928. Again increased, it becomes 0.903, and you can see that as the molality is increasing, the mean ionic activity values are decreasing. Or you can say it in the other way, when the solution is very dilute, the mean ionic activity value approaches unity. See, okay, 0.9 means it is almost equal to 1. Okay. Now, at lower concentrations, the mean ionic activity coefficient values approaches unity. That is what we get from the experimental details. Now, again, when we plot mean ionic activity coefficients against square root of molality, it has been found that, see, at the lower values of concentration or molality, the value approaches unity, and as the concentration increases, it deviates from the value of unity. So, again the deviation always increases with increase in concentration. Okay. And mean ionic activity is the mean ionic activity coefficient multiplied by molality, as we have seen earlier, and the activity coefficient value is low. If this value, that is gamma plus or minus value, is low, that means if this is low, activity is lesser than molality, because if this value is low means less than 1, it is a fraction multiplied by molality, and therefore, the value of this will be lowered. When it has got high activity, that is its value is high, activity will be greater than molality. Okay. Now, activity coefficient values also deviate at higher concentrations. This is all because of interionic attractions existing within the electrolyte. Now, to conclude, we have been seeing in this session activity coefficients of electrolytes. Activities and activity coefficients are related like A is equal to activity is equal to activity coefficient into molality. Molality means it is a form of concentration, expressing concentration. Then mean ionic activity is equal to A plus or minus is the product of activity of the cation raised to the power x into product of activity coefficient of the anion raised to the power y. The mean ionic activity coefficient is related to molality as mean ionic activity of an electrolyte is equal to the mean ionic activity coefficient multiplied by its molality. Thank you.